Students, today we are going to study compound microscope. Compound microscope is an optical device used to see magnified images of tiny objects. A good quality compound microscope can produce magnification of the order of 1000. Now, see the construction of compound microscope. It consists of two convex lenses of shorter wavelength arranged coaxially at the ends of two sliding metal tube. Objective. We are having two convex lenses. First one is objective, another one is eyepiece. Now come to objective. It is a convex lens of very short focal length FO. Here you see it is principal focus and distance between optical center and principal focus is called focal length FO, and small aperture. Aperture is very small. It is positioned near the object to be magnified. Our object is AB. Eyepiece. It is a convex lens. See, it is a convex lens of comparatively larger focal length FE, E for eyepiece, and larger aperture. See, larger aperture than the objective. It is positioned near the eye for viewing the final image. The distance between the two lenses can be varied by using rack and pinion arrangement. Now come to working. When the final image is formed at the least distance of distinct vision. See, here we are having final image A double dash B double dash. It is final image. It is formed at D. D is least distance of distinct vision. The object AB, AB is our object. The object AB to be viewed is placed at distance UO. U object distance, O for objective for this lens. So, AB is placed at a distance of UO slightly larger than the focal length of the objective. See, it is very close to principal focus of objective, but it is not at principal focus. It is slightly, see, the distance is slightly larger than the focal length. The objective forms a real, inverted and magnified image A dash B dash. See, object AB is placed at a distance of UO, O for objective, and for this object, for it AB, A dash B dash first image is obtained and the image A dash B dash is real, inverted and magnified. Okay. Now, the objective forms a real inverted and magnified image A dash B dash of the object AB on the other side of the lens O, O for objective. The separation between the objective and the eyepiece is so adjusted that the image A dash B dash lies within the focal length of eyepiece. See, distance between these two lenses are so adjusted that first image should be between optical center and focus of eyepiece. The image A-B- acts as an object for the eyepiece, which essentially acts like a simple microscope. The eyepiece E forms a virtual and magnified final image A-B- of the object AB. AB is object and A-B- is final image of the object. Clearly, the final image A-B- is inverted with respect to the object. Here you see, it is final image and it is inverted with respect to the object AB. Now, we are going to calculate magnifying power. We know that magnifying power M is equal to beta upon alpha. How to define magnifying power? You see, magnifying power of a compound microscope is defined as the ratio of the angle subtended at the eye by the final virtual image to the angle subtended at the eye by the object when both are at the least distance of distinct vision from the eyepiece. That's why mathematically we can write M magnifying power is equal to beta upon alpha. Here alpha and beta are small angles, so we can write M is equal to tan beta upon tan alpha. Now, for magnifying power M, you see tan beta. Tan beta is equal to this A dash B dash. It is height or size of the first image divided by base. Base means EB dash. It is equal to UE. So, substituting for tan beta, we can write H dash upon UE. E for eyepiece. Now come to tan alpha. Tan alpha. It will be AB. AB is object and H, if H is height of the object, we can write for AB, it is H divided by base of the triangle. Base is D, least distance of distinct vision. So for this base, we can write D. So we have M magnification is equal to H dash upon UE divided by H upon D. Or we can write H dash upon H into D upon UE. Now you see, size of the image upon size of the object, it is magnifying power for objective. So for this quantity H dash upon H, we can write MO, O for objective, and for this D upon UE, we can write ME. E for eyepiece, and as usual M is magnifying power. Now here once again I have written CMO is equal to H dash upon H. Now from the definition of magnification or magnifying power, we can write H dash upon H is also equal to VO, O for objective and V is image distance divided by UO, object distance, O for objective and ME for D divided by UE. As eyepiece acts as a simple microscope, eyepiece, it is eyepiece. Eyepiece acts as a simple microscope. So, magnifying power for eyepiece ME is equal to D upon UE can be written as 1 plus D upon Fe. It is magnifying power for simple microscope. Now, substituting 1 plus D upon Fe for this quantity, we can write M is equal to V naught upon U naught into 1 plus D upon Fe. Now, as the object AB, this object AB is placed close to focus of the principal focus of the objective. So, we can write object distance UO is nearly equal to minus of FO, F, small f. It is focal length for objective, O for objective. Also, image A dash, B dash, first image is formed close to the eye lens, this eyepiece or eye lens, whose focal length is short. Therefore, VO can be written as L, where L is length of the microscope tube. Using L for VO, we can write MO is equal to, since we are having MO for objective, magnifying power of objective is equal to VO divided by UO. So we can write MO is equal to L upon minus of FO. Minus sign we are using for sign convention. We have to use sign convention. Therefore, our magnifying power for compound microscope, finally we get M is equal to minus of L upon F naught into 1 plus D upon Fe. Here, this magnifying power is for final image at D, at least distance of distinct vision. Now, compound microscope, when image is formed at infinity. Here you see we are having two convex lenses, objective, eyepiece. AB is object, FO principal focus of objective, FE principal focus of eyepiece. Object AB is placed very close to the principal focus of objective. UO is object distance, VO is image distance. Distance between optical center and first image, UE, it is equal to focal length of eyepiece. Now, come to magnifying power of compound microscope when the final image is formed at infinity. The magnifying power of a compound microscope is defined as the ratio of the angle subtended at the eye by the final image formed at infinity to the angle subtended by the object. When the image A dash B dash lies at the focus of the eyepiece, UE is equal to FE. The final image is formed at infinity. Here you see the distance between these two. This distance is so adjusted that first image of the object AB, first image A dash B dash should lie on the principal focus of the eyepiece, so that we can write UE, object distance for eyepiece, is equal to FE, focal length of eyepiece. Now magnification due to objective. MO is equal to H dash upon H, which is also equal to L upon minus of FO. Angular magnification due to eyepiece, ME is equal to D upon FE. Total magnification when the final image is formed at infinity, that is M is a product of MO and ME, that is M is equal to MO into ME. Substituting the values, we get M is equal to minus of L upon FO into D upon FE. It is magnifying power of compound microscope when the final image is formed at infinity. Obviously, magnifying power of the compound microscope is large when both FO and FE are small.